Well, welcome to the last morning of this workshop. And it's my pleasure to introduce the first speaker of the day, Daniele Dorigoni from Durham, who will speak about any novel results in n=4 super Yang mills with classical gauge groups.
Thank you, Marcel. Very good. Thank you all for showing up on the last day. Thank you to the organizer for inviting me here. It's actually a pleasure to be back in Cambridge. It's been such a long time. I will be talking about a bunch of stuff that we've been working together with Concao, sitting over there, Michael sitting over there. But let me start with something light. So if it works. No. All right. Should be working now. Very good. So yeah, we have heard a lot of times in this conference that we have to cross the bridge. And then what? Well, I'll give you a suggestion. You can turn left after you cross this bridge, and you go You pop up in King's College. You enter King's College, and you find the chapel. And then I'm sure that everyone will spot it, that there is a fundamental domain of SL to G. And this is shamefully stolen from Michael's Eurostring. For the one of you who participated, there was a little Easter egg on the webpage that Michael did himself. If you clicked on the image, you would actually get this picture. All right, so let's start with the... Oh, good. So let me start with an integral, and then I will give you the physics later on. So whatever Pestun did something great. He told us how to compute certain quantity exactly. So in here, I'm writing what is called the n=2 star S4 partition function. And if you don't know what any of the words means, don't worry. It's just an integral over a bunch of stuff that I'm reviewing in here. So in this talk, I'm going to be talking about classical gauge groups. Actually, we're really going to be dealing with algebras, but bear with me. So we're going to be dealing with SU, SO, or USP groups. So this GN stands from one of the three. The integration variables are parameterized in the r-dimensional Cartan subalgebra of whatever we're discussing, and we're integrating over these real variables. This BGN is actually already going to the diagonal basis, is just the van der Monde determinant of these Cartan elements. So if you wish, for SUN, is just the product of AI minus AJ squared. Change the group, this van der Monde changes slightly, but still same sort of functions. And then we have what we would call, in physics terms, the classical action, e⁻² pi tau 2 AA, where this is the killing form. And this function is a function of this little m, which is just some positive parameter. If you're familiar with the context, this is just the mass that you give to the hypers to break n=4. And the coupling constant, which is going to be our modular parameter. So I brought it in here for the following. So I'm always going to be writing, I apologize to mathematician, I don't write it as x plus iy, I write it as tau1 plus I tau 2, and y is pi tau 2. The reason is that when we use this variable y, everything will come out with nice transcendentality properties. Very good. And in physics language, the imaginary part is the inverse of the Yang-Mills coupling. There are another couple of building blocks that I need to tell you. This ZGN perturbative is what we call the one-loop determinant, is this combination of product over roots of a certain combination of Barnes functions. So it's a very concrete function that you can compute in principle on all groups. And here I put you an easy example for SUN is this particular product again of combination of Barnes functions. And then the last bit is Nekrasov instanton partition function, which contains all non-perturbative terms. So you can write it in a Fourier mode decomposition is 1 plus a sum of q to the k, e⁻² pi I k tau, times some function of the instanton number, and again, these parameters. For SUN, for k = 1, the function is of this type. In general, for arbitrary k, there are formulas for Nekrasov. For GNs arbitrary, there are some formulas. There are also some formulas for exceptional groups. You can write them as contour integrals, but let me not get into that. So what we want to compute is this particular object. We want to take a Laplacian with respect to tau, two derivative with respect to this parameter m, of the log of this matrix model. And at the end, we want to set n equal to 0. So this is the quantity that we want to compute. So let me tell you why we want to do it. But if you don't care, I'll leave you a little exercise. For SU2, there are all the building blocks in here. You can also forget about the instanton if you want the asymptotic expansion at the cusp. Little exercise, compute the asymptotic expansion. And you will get something which looks rather nice. Zeta 3 over y, zeta 5 over y squared, zeta 7 over y cubed, and so on. Where again, y is pi tau 2. So this is why I wanted to use this variable, because in this way you only get single valued zetas. And actually, for this correlator, you only get single zetas. You don't get any multiple zeta values. So why should we care? Well, now I'm going to say a bunch of words. I'm not going to enter the details. Apologies to the non-experts. So this object that we just computed has to do with some particular n equal to 4 correlators. In particular, you construct what is called the O2 correlator. You just take trace of phi I, phi j. You soak up the indices with some null polarization vector. And this is a protected operator. That's dimension 2. It's a half BPS operator, and it's what usually you call 0,2,0 operator. And now you consider the 4-point function of this operator. This is a non-protected quantity, O2, 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 4 of them. And now you have a nice factor overall, which is fixed completely by superconformal invariance. So we actually don't really care about this one. The factor that we really care about this is this function in here, which is really a non-trivial function of both the crossing ratio U and V, the coupling constant, the gauge group. So this is where all the fun lies, but it's also where all the complications are. And why is it important? Well, because this O2, O2, O2 sits in the same multiplet as the energy momentum tensor, and the gauge gravity correspondence tell us that this object is related to the graviton scattering. And in this conference, we've already seen a bunch of talks on genus 1, some talks on the generation of genus 2, and so on. So you make connection by studying this operator with 4 graviton scattering in type 2b. What happens is that by considering that particular combination of derivatives that I told you about, in this really nice paper by Binder, Chester, Put, Fu, and Wang, they've shown that actually this combination of derivatives of Pestun gives you the correlator O2, O2, O2 that I told you before for some special polarization, integrated with a very specific measure that was too lazy to write out over the 4-point insertion. So this quantity that you can compute in localization gives you some handle on this complicated integrated correlator. So this is why we actually care about it. There is another object that you can actually study for mass derivative log, and you bring down the same O2, 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 but integrated with respect to a different measure. So although it looks very similar, this object in here is a way harder beast. We are studying it with Konkao and Michael. In the asymptotic expansion of this guy, you also get bilinear synod zetas. You don't get anything more than that, though. You get single zetas, binillion in zetas, and that's it. But it's not really clear what type of modular function this is going to be. Very good. So let me go back to being a little bit more understandable. So this is the quantity that we're going to be studying, and we expect these integrated correlators to be invariant under what is called Genome duality. So I'm going to review what it is. For the maths audience, roughly speaking, it's going to be SL2, but a little bit more specified. Very good. Wishful thinking. Good. So we studied this object in here. What did we find? We find this particular expression for these integrated correlators. A lattice sum of an integral of these functions B1 and B2. I'm going to give you concretely some SU2 examples, sorry, SUN examples later on, but they're very easy functions. They're just rational functions of this integration parameter T. And then the dependence on the coupling constant is very easy. E to the minus, the lattice sum, usual m plus n tau squared over tau 2. And also this other lattice sum, m plus 2n tau squared over tau 2. Yeah.
That's very different if m equals n equals 0. Is that
Good, excellent. In general, very good question. In general, here you would like to, or at least when you write Eisenstein, you'll avoid it. In here, you can actually put m equal to n equal to 0. This exponential drops, and the integral of these two functions are finite, and they're actually nice. I'm going to write something later on. Thank you. Yeah, absolutely. In principle, you might worry that, for example, when you write the Eisenstein, you don't include that one because it's divergent. These contributions are not. They give you just, for example, for SUN, you get n minus 1 over 8, something like that. Thank you. Other questions? Yes, please.
The second term seems to say that you will only have gamma 0, 2.
Excellent, thank you. I'll get there. Yeah. So I need to tell you, in here I wrote the general formula. What's going to happen is that in some cases, gamma 0, 2 will be the relevant symmetry. In other cases, SL2. Thank you. Yeah. I need to tell you, well, I need to tell you know it already, but I need to explain a little bit more what I mean with that one. Thank you so much, Bjorn. Very good. So this expression in here, as far as I know, is the first example that we got of a quantity n equal to 4, which is valid for all values of n. So we have expression for any n, SU2 all the way to SU infinity, SON, SO2 all the way to SU infinity, is valid for all classical gauge groups. This is a function in the upper plane, so you can put your coupling constant to be whatever you want. It's not weak coupling Young-Mills, it's not strong coupling Young-Mills, it's every value. And as I'm going to comment in a second, is actually Monton-Olive GNO covariant. And this is going to go back to your gamma 0, 2 question. Yeah. So what is this GNO duality? Well, in n equal to 4, with a gauge group Gn and this coupling constant, electromagnetic duality was at the beginning the only duality we knew, or one of the few duality we knew, and it was generalized to something a little bit broader, what is called Monton-Olive or GNO duality. And the idea is as follows. So if I give you a quantity, like the original integral that I wrote before, for a group Gn and a parameter tau, I expect it to be invariant under T transformation, where I don't change the group, and I shift the parameter tau to tau plus 1. However, I also expect to have a duality in which I give you the integral over a certain group Gn and coupling tau. You give me the integral over what is sometimes called the Langland duals group Lgn and coupling constant minus 1 over r tau, where r is the square of the ratio between long and short roots of the algebra. Notice that in here, the integral is over the same Cartan. In here, I'm really giving you two different integrals. So this is the list of Langland dualities. However, we are actually only going to be focusing on the classical ones. And furthermore, I don't even need to say group, because if you remember at the beginning, I wrote an integral over the algebra. So for this particular observable, we actually really care about the Lie algebras. The duality extends more. So there are extended operators which really care about the global structure of the group. The duality is the one that I wrote you before. But for the particular integrals I wrote before, it was an integral over the Cartan subalgebra. Hence, we only care about the algebras.
So
yeah.
That just the normalization of the partition function? The overall normalization?
Oh, yeah, but we are taking a log of the partition function. And then, yeah, thank you. Absolutely. Yeah. No, in general, you do expect, like, if you give me other quantity, hello, Kat, there should be really the group behind it. Yeah. The normalization, I didn't even write it out because we are taking the log and it drops out. Yeah, thank you. Very good. You have questions? Yeah.
What is protected and what is not? So you
yeah.
Protected quantity.
Yeah.
Produce a quantity just by differentiation, and you say it's not protected. Is it?
I didn't say it's not protected. I said the 4-point function. So some of the question is, what is protected? Was it not protected?
Right.
The 4-point function of O2, 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 O2 is not protected.
But the integrated thing.
Very good.
But it's just some Taylor coefficient of a protected quantity. That's
you're integrating over the insertion points. So think about in superconformal blocks, okay? I'm taking a very weird combination of integral of superconformal blocks. I have no idea what this is doing. I mean, it's selecting. So it's going to make it clear a little bit later on when we make connection with type 2b. It selects certain quantities of higher derivative corrections which are protected. But from the point, it's a very good question. From the point of view, what are we really doing when we are taking an integral over a 4-point function? What is really selecting of the superconformal blocks? it's selecting some quantity which is protected. Clearly, in the case of a protector, right, you're preserving some Q homology, and what you're getting out is protected in that sense. Yeah. Which part of the non-protected, unintegrated O2, 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 O2 you're actually selecting? Yeah, that's a good question. Thank you. Very good. So this duality that I was telling you about, so we expect the integral that I wrote before to be invariant under this duality. So let's start with something easy. Let's start with the case in which I was doing SU or SO. So this duality tells us that under T, G doesn't change, and under S hat, also it doesn't change. Because you see that the Langland duals is the same. SUN goes to SUN, SON goes into SUN. Furthermore, the ratio between long and short roots in these two cases is 1. So this S hat transformation is the standard S transformation. You don't do anything to the gauge group. You started with an SU integral, you end up with an SU integral, and you take tau and you send it into -1/tau. So I don't need to convince this audience that these S and T generate SL2Z. So in these cases, we expect the quantity that I told you at the beginning to be an SL2Z invariant quantity. Going back to Guillaume's question, what does it happen in the other case? Actually, no, sorry. First, let me show you that. So for GN, SUN, or SUN, in the formula that I wrote you before, the second term, the one that you were worrying about, actually, we found that is 0. So the whole expression can be given in terms of this lattice sum. And again, I don't need to convince this audience that this expression in here is clearly SL2Z invariant. So GNO duality works well. Tau going to tau plus 1 is a triviality. Tau going to -1/tau is also not that difficult. This is an SL2Z non-holomorphic invariant quantity. For the other two cases, the story is a little bit more interesting because under this transformation S hat, Gn and the Langland duals actually change. In this case, the ratio between the roots is 2. So this duality tells us that we should expect in the SUN and SON odd case, sorry, in the SO odd and the USP case, that this correlator does actually something. Under T, nothing changes. Under S hat, the USP correlator must transform into the SO odd correlator, and the SO odd correlator must transform into the USP correlator. However, you also need to change the coupling constant tau into -1/2 tau. So this is a covariance, if you wish. The correlator in the USP theory is related to the correlator in the SO theory by taking tau into -1/tau. So this is not a symmetry, this is a duality. You're really telling me that two different integrals over different algebras are related by this tau going to -1/tau. But if you consider S hat, T S hat, this brings you back to itself. S hat makes me move from one side to the other, S hat makes me move backwards. So T and S hat, TS hat, generates the self-duality group, which is indeed gamma 0, 2. So if I do these two transformations, I expect the correlator in USP to be invariant under gamma 0, 2, and the correlator in SO to be invariant under gamma 0, 2. And in fact, this is what happens. For the SO odd and USP, we found that these two rational functions are related. B1 of SO odd is B2 of USP, and B2 of SO odd is B1 of USP. So under this transformation in which I send USP to SO, these two terms flip. But you see from the exponent that because of the 2 that you pointed out, when I send tau into -1/tau, this exponent goes into this exponent. And so under this transformation, we flip these two rational functions, we flip these two exponents, and so the SO correlator is related to the USP correlator. Furthermore, I'm going to show you in a second, but it's clearly not that difficult to see that this expression is invariant under gamma 0, 2. Any question on this part? So, how to make it a little bit more manifest? We can actually, it's not necessary. This is clearly a modular invariant function or gamma 0, 2 invariant function, but we like to expand stuff. So if I expand these rational functions around the origin, there's a power series, there's a convergent power series expansion. and I can integrate term by term. I don't have to worry about the m equal to n equal to 0 term because it gives me a constant overall, which we actually can compute. But then when we integrate term by term, you just do the usual integral of the gamma function, and you generate the non-holomorphic Eisenstein series, either with parameter tau and tau bar and index S, or with parameter 2 tau and 2 tau bar from this guy in here. So this one, just not to be confused, these are the non-holomorphic modular invariant Eisenstein series, that mass forms in here. They're not the holomorphic modular forms. So if you do this calculation, then you get this non-holomorphic Eisenstein series. In the SU case, or in the SO even case, the second term is missing, so you don't have the second Eisenstein, and this is clearly a modular invariant function. In the USP or SO odd case, you have the second Eisenstein, and hence the duality is really gamma 0, 2. Sorry, the symmetry is really gamma 0, 2. If you wish, you can actually write this expression as a spectral decomposition. So it was a nice paper by Collier and Perlmutter. They were caring about some ensemble averages. I don't understand why, but I'm not going to enter in that. But basically, you don't have to do this expansion. This is a modular invariant function that you can rewrite in this way.
They can prove it's not enough.
Very good. Not a proof. Yeah. You can check that if you don't put, that's a very good point, you don't have the non-holomorphic cusp. You can check that the instanton part coming from the Eisenstein matches the localization result. Yeah. But I wouldn't say it's a proof. Yeah. In particular, the other correlator that I mentioned before, very likely is going to contain these non-holomorphic cusp forms. Yeah. And nobody knows what to do with that. Yeah. Very good. So let me give you some more concrete results. Let me stick to SUN. The story for SON and USP is very similar. The formulas are just slightly different. So as I mentioned, this BSUN, now I only have the B1, so let me drop the index 1. These B of SUN are some rational functions. They're just some polynomial divided by t plus 1 to some power. And actually, this polynomial can be written in terms of Jacobi polynomials. It's not important. To give you some examples, SU2, you get this expression, SU3, and SU4. And you notice that these are some nice palindromic polynomials. 3 minus 10, 3, 2 minus 11, 14 minus 11, 2. So this is actually something stronger. All of these rational functions satisfy this inversion property. I'll come back to that in a second. You can put all of them together. Well, if Don were here, he would tell us that generating series indeed are nice. Every time you have something that depends on a parameter, put all of them together. And you get this reasonably, well, depends, nice or not nice, depending on how tolerant you are. It's not particularly ugly. You just add a bunch of branch cuts. So this generating series tells you all of this integrand for this SU correlator. It has a lot of properties. Well, obviously, the way we do it is so that if we take the residue at 0 of the n plus 1 power, we get the SUN function. The integral over t of this generating series, which is identical to the question that Sal was asking before. If I set m equal to n equal to 0, the exponential factor drops, and so I need to worry about the integral over t. It's finite. And it's given by this expression that you can expand around the origin. So the term that you were worrying is just this one, n minus 1 over 8, and something similar for SO or USP. So there is no singularity really at the origin of the lattice. The other property is that if you integrate this 1 over root t, you get 0. More properties on this generating series. It has this inversion property, t going to 1 over t. This is directly related when you translate it back into the spectral decomposition to the reflection symmetry S going to 1 minus S. The reason is not too difficult to see from the expression that I wrote in terms of Eisensteins. Very good. So in here, I expanded around the origin and I get the Eisenstein ES. However, if you do t going to 1 over t, you will get the Eisenstein E1 minus S. So the expression should be the same, and then you get the same function. Very good. The other, which is a little bit weird. Yes, please.
There is not only one that converges, however. No.
Yeah. No, exactly. You need to get, well, it depends. So if the expression in terms of Eisenstein, neither of the two is convergent, is really either the lattice sum that is convergent or a spectral decomposition, which is convergent. However, formally, you can close the contour in the spectral decomposition from the positive, and you get E2, E3, E4, or you can close the contour on the negative, and you get the duals one. But neither of these expressions is a convergent expansion. But the function that I give you is a function. Yeah. Thank you. Very good. So Z, if you remember, is the little variable that tells us which SUN we are dealing with. If you invert it, it's like taking n to minus n. So this actually tells us that the SUN correlator with coupling constant g square is related to the SU minus n correlator, coupling constant minus g square, whatever SU minus n is. So there are some of these dualities in string theory. It actually does work also for SO. So SO even goes to USP. Good. So as I was saying, formally, you can indeed expand this correlator. And the nice thing is that at finite n, we only get integer Eisenstein series. As we're saying, I'm going to expand and close the contour of the positive, so I get the good Eisensteins, E2, E3, E4, and so on. However, the right-hand side in here means absolutely nothing. There is no conversion whatsoever that I'm assuming in here. It's just a nice formal expansion. This is actually how we found the correlator. We noticed that in the expression that I wrote before, this is the asymptotic expansion at the cusp. And now this term, zeta 3 over y, zeta 5 over y squared, zeta 7 over y cubed, recognize that they're exactly of the same type as the zeta 3 contribution coming from E2, the zeta 5 contribution coming from E3, and so on. However, the reason why this object makes absolutely no sense is that at the cusp, E2 and so on doesn't just have the y to the 1 minus s, it also has the y to the s. The interesting thing is that if in this formal expression, you take all the positive powers and you resum them and you expand them at the cusp, you actually get identically the expansion of all the negative powers. So morally, what's happening is that in E2, you take the coefficient of y to the 1 minus s and you double it. And the expansion that you get is this one. However, you don't have to do it. You just need to take this expansion and expand it at the cusp. And it gives you this expression in here. For SUN and higher, the expression is still of the same type. The only thing that changes are the number in front. Particularly, as I was mentioning, we don't get anything weirder than single odd zetas. That is not true for the other correlator that I'm not gonna write out. Over there, you also get bilinears in odd zetas. This at finite n. The story at infinite n changes dramatically. At infinite n, from this expression, we can easily take a large n expansion. It's a power series in fractions, n½ and -½ and so on. And now the coefficients are polynomials. Well, actually, they're just linear polynomials in half integer Eisensteins, E3 halves, E5 halves, and so on. These are the only terms that you get from the asymptotic large n expansion here. And now we connect back, and I make a connection with what Samir was saying before. The large n expansion at fixed tau, it's still modular. We have not taken a 't Hooft coupling limit. When you go in the 't Hooft coupling limit, you lose modularity. In here, we are really keeping tau. So you should really be able to make a connection with type 2b, a low energy, where now the modular parameter, you can really think of it as the axiodilaton. In type 2b, the effective Lagrangian has a power series expansion in alpha prime corrections, higher derivative corrections. And you can translate powers of alpha primes into powers of n. The terms that I circle in here, n to the half, n to the half, n to the -½ n to the -½ are exactly the coefficients of these higher derivative corrections that were found in a completely different calculation by Michael and collaborators Pierre as well. However, you will notice in here that I'm jumping from n½ to n3 halves, while instead in here, there should be a term which goes like 1 over n. So this goes back to Samir's question. What is this integrated correlator really selecting? Well, the answer is it's not really clear. Furthermore, in here, you have higher corrections, entry halves, and so on. However, if you keep on going here, all of these corrections are not BPS any longer. But somehow this integrated correlator selects some combination, whatever it is, that is BPS invariant. These red terms, if you actually study the other correlator that I mentioned, will actually appear. And the coefficient is one of these generalized Eisensteins that Kim was talking about, is the delta minus 12 equal to E3 half squared. You also get other type of generalized Eisensteins, precisely the one that Kim was talking about, with half integer sources, E3 halves, E5 halves, and so on. But again, there are some proposals for inhomogeneous Laplace equations for these higher derivative corrections, but I'm not really sure how justified they are because these terms are not BPS protected anymore. Very good. The other interesting thing that we have found is that if we take this SUN correlator, we can actually do a large N expansion a little bit more detailed. So in here, the large N expansion was only containing a power series in N. For fixed value of tau, you can think of this one as really a power series in N with some coefficients which are given by numbers. This is an asymptotic power series in 1 over N, and it does need exponentially suppressed corrections in N to actually make sense. We didn't have to do that. We actually did the saddle point analysis in here. Well, not quite, it's to appear shortly. And we found that actually the large N must also include some exponential suppression in N of this type. And I would actually be curious to see if this type of non-holomorphic modular invariant functions has appeared in some other problems. So this is clearly modular invariant. It looks like, as Axel told me, it looks like some sort of regulator. You see there is some exponential factor that makes this series converge of the usual Eisenstein type of term. I'm not sure, I don't think they solve any sort of nice Laplace equation, but we haven't really explored this part. I should also comment that there was a very recent paper by Yasuyuki and Okuyama. What they did, which I'm not going to mention today, they actually studied a little bit more in detail not just this large N limit, the toothed large N limit. So in the toothed large N limit, you can use some resurgence argument to actually compute the exponentially suppressed corrections that are needed. Our results, when you translate it back into the tooth limit, reproduces the results. Another thing that I would like to mention, if some of you are around from the 5th of September, there is another Newton Institute program going on resurgence, and it's going to go on all the way to December. The other thing that I want to mention is that we found some very interesting Laplace difference equations satisfied by these correlators. So let me go back to the previous correlator where it's easier. Good. So in here, for the SUN correlator, we got this nice expression written in terms of Jacobi polynomials. Jacobi polynomials satisfy a 3 terms recursion relation. What we have found is that the correlator satisfies this intriguing Laplace equation, where you get the Laplacian with respect to tau acting on the SUN correlator relates to the SUN plus 1, the SUN, and the SUN minus 1 correlator. And very similar equations for the SO and the USP. And this number in here, C, 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 are just the central charges. So these are sort of like total-like equations satisfied by this correlator. I would be curious to discuss if anyone has any idea of the stringy origin of something like that. Clearly, you're changing the number of branes, but also I don't know what really the derivative with respect to tau is doing. But this is something that we have found for these particular integrated correlators. From a practical point of view, this equation tells you that everything is determined once you know the initial condition. Once you give me the SU2 correlator, everything is fixed. The only thing that you need to impose is that the stupid groups, SU1, SO1, and so on, they all vanish. So if you do that, you can actually use this Laplace equation as a recursive way to find the SU3, SU4, and so on correlators. Very good. So you can start solving the SO even. You plug in n equal to 2. SO2 is trivial. So you get SO4, SO2, SO0 is trivial. Nothing, SU2. Very good question. Yeah, I don't know. I mean, they're clearly consistent. So we checked actually that, of course, these relations are consistent perturbative and non-perturbative. But from the causal point of view, I mean, it's really weird, right? You are changing the dimension of the integrals. You're giving me different dimensional integrals, and they're related. So we do have a proof from the matrix model point of view. Well, sort of. It's not really clear what this derivative really does. But in here, you're relating matrix model with different dimensions. Yeah. Yeah, I'm not sure. But we have checked that indeed they're consistent with the causal partition function. They're consistent in perturbation theory. Yeah. Well, actually, once this ansatz, so this is a conjecture, of course, we don't have a proof. Well, sort of. We have checked this one from the perturbative point of view, but also from the instanton sector. Once this is given, the Laplace-difference equation is proven using the 3 terms recursion for the Jacobi. Yeah. Other questions? Good. So now you can start using this Laplace-difference equation to solve the SO and the USP correlators in terms of the SU correlator. Because you see in here that there is a sort of source term that relates the SO correlator to the SU correlator and the USP to the SU. The only thing of the USP is that you have a 2 tau. So we get the SO4 correlator is twice the SU2 correlator. The SO6 correlator is the SU4 correlator. Well, not surprised. These are the expected Lie algebra relations. SO4 is 2 copies of SU2. And so you get this factor of 2. And SO6 is the same as SU4. One instead, as I was saying, in general for hires, you just get the SO correlator as a combination of SU correlators. You can do the same for the SO odd and the USP. Particularly, you find that the SO5 correlator is the same as the USP4 correlator. But again, these are expected Lie algebra relations between these two groups. And these correlators now takes a slightly different form. They are given by the SU correlator at tau and the SU correlator at 2 tau. As expected, as Guillaume was asking before, these correlators in here are not expected to be SL2Z invariant. They're expected to be gamma 02 invariant. So if you give me a function of tau, which is SL2Z invariant, and you multiply by 2 tau, you get something which is gamma 02 invariant. Furthermore, not only this is, so this is really the symmetry of the correlator, but we still expect this Olive-Monton duality. So SO7 and USP are related under this S transformation, S hat transformation. If I take the SO7 correlator and send tau into -1 over tau, -1 over 2 tau, I should get this correlator. And in fact, you see in here that the first terms are the one in which you get tau. When you send tau to -1 over 2 tau, you get these terms in here. And these are the correlators at 2 tau. When you send tau into -1 over 2 tau, you get the second term. So this is how the covariants work. Very good. I'm doing excellent with time. I hope you're not gonna be angry that I'm finishing. Yeah.
They're all related to SU.
Yes, 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 yes. You can solve recursively these equations given the initial condition, and they're all related to the SU correlators. Yeah. Yeah. Sorry, you were asking? No. Perfect. So let me conclude with some comments and some open questions for which I don't have the answer to. These correlators that I presented are a non-trivial example, the first one that I know of, in which it's really a quantity in n equal to 4 super-Young mills, which is non-protected. Well, it's protected in the sense that it's coming from supersymmetric localization, but it involves a non-protected quantity. And it's valid for all values of the coupling constant, all values of n, And we found the expression for all classical gauge groups. As I was saying before, how did we actually find it? Well, at the beginning, we checked with perturbation theory. As I mentioned before, the same was actually true for all the other groups. Asymptotic expansion suggested that we had to expand in terms of Eisenstein. We used also results by, I think I wrote it before, for SO. That was some really nice paper as well by Chester, Aldai, and I'm forgetting someone, so I don't want to do that. What is it? Very good. Aldai, Chester, and Hansen. They actually did the SO and USP, perturbative. And over there, we checked that indeed it was consistent with an expansion in terms of Eisenstein and Eisenstein of 2 tau. But then after that, we actually used Nekrasov partition function to check, given our prediction, if the instantons were matching. So for SO and USP, there are results by Below, Fucito, and Morales on Nekrasov partition function with the classical gauge groups. There are also some results with exceptional gauge groups, but we haven't experienced, well, we haven't really done anything with that because the study over there is a little bit more complicated. So for exceptional gauge groups, there are some which are S-dual. So you really expect them to be SL to Z invariant functions. But F4 and G2, the self-duality is something weirder. It's some Hecke group. So we don't really know what class of functions one should expand over. Because of course, we have only access to the perturbative data, and then you try to come up with some modular completion in terms of some class of function that you expect to have the right symmetry. In this correlator for classical gauge groups, the Eisenstein were the answer. For this F4 and G2, it should be something which is invariant under Hecke group, but I don't know what. What is the string theory origin of this lattice sum representation? This is something else that we would really like to understand. The polynomials that I wrote before, they had integer coefficients. So somehow they're counting something, but I don't know what they're counting. There should be some, maybe coming from 6D, origin of these lattice sum representations. And same, what is the string theory origin of this Laplace-difference equation? So you are changing, as we were saying before, you are changing the dimension of your matrix model. You're changing the n of the gauge theory. So somehow you're considering a theory with different number of branes. I don't know how one could construct such Laplace difference equation from really string theory. The other integrated correlator is also a very interesting question. As I mentioned before, for this one, we have full access to the perturbative expansion at the cusp. And the only thing that changes is that now you get single zeta values and product of single zeta values. That's it. There's nothing else. It might be actually that the right expansions are the generalized Eisenstein that Kim was talking about, but with integer sources rather than half integer sources. Yeah. And finally, also because Hugh is here, he's an expert on that, we give an exact formula for this integrated correlator. However, one can take the 4-point function of O2, 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 O2 and expand it in superconformal blocks. And although I didn't write it out, it's a very well-defined integral over the 4 insertion points. I didn't write the measure. It's a very simple measure, U over V to some power. What does it happen if you integrate the conformal blocks one by one and then compare against our formula? Can you actually use this formula to obtain some information, maybe at large n, of the anomalous dimension dependence on the coupling constant? So in this direction, there was already some preliminary result by Chester, but he was using numerical. He was numerically evaluating the integrated correlator, numerically evaluating ours, and matching with the bootstrap. Yeah. Very good. That is it. I spoke way too fast, but I'm sure you're not gonna be angry for an early coffee.
Daniele, thank you very much. That was a really nice talk.
Thank you.
I'd like to ask if anybody has questions.
Thank you for your talk. Yeah. When you take those integrated correlator, in principle, you can also relate them to integrated Winton diagram on the bulk. So can you trace back of what it would be in the flat space limit as an integrated 4-point function?
Very good question. So in fact, I lied a little bit about in here. So you have to do 2 things indeed. First, you have to understand what the integrated correlator does. And secondly, you have to understand the flat space limit. So in here, what I presented is really the flat space limit one. So there is this procedure of taking the Melling transform and taking the flat space limit, and you are selecting somehow, again, it goes back to Samir's question, you're selecting somehow some of these coefficients. Yeah, but it's not really clear to me how much of the flat space, because this is on S4, right? So it's really, you're really computing ADS5 cross S5 correlators integrated. And then if you take the flat space limit, somehow you're selecting something of this flat space limit 4-point function. Yeah.
But you cannot get back the integral first.
No, I don't think so. Yeah. That's a really good question. Thank you.
Your 4-point function, which you start from, has rather nice crossing symmetry properties. Is that built into what you're integrating it against, or?
Oh, good question. Concau, do you remember the measure by heart? It must be. Where is it?
Okay, so you're not sort of projecting out some bit of the measure because of crossing symmetry.
I don't think you're projecting out anything. So this was the first. Oh, maybe you're projecting. But the reason why it's so simple is that you're projecting out a lot of stuff. I actually think that all the superconformal blocks do contribute in here. Yeah, but in a very easy way. In particular, I should say, in the expression that we got, there are no instanton anti-instantons. There are instantons, there are anti-instantons, but there are no instanton anti-instantons.
Yeah.
When instead there are in this expression.
I mean, if you expand it over conformal blocks, this will only be convergent within a certain domain.
Yeah.
I'm not sure precisely what. And then, of course, the crossing domain is something which converges in a separate area.
In fact, I think that in Chester's paper, he had to fold the domain of integration precisely as a 3-time folding of the domain that you're talking about, because then it was really evaluating numerically the integral over this domain of a given superconformal block. Because of course I can use your formula for the superconformal block, take this integral, and that's a well-defined integral after I brought it to this domain. Yeah, but he did it numerically.
I mean, you started off from a very specific 4-point function for these O2 operators. Of course, there are loads of half PPS operators for any given n, not just n equals 2. I mean, is there any hope of working out more general integrals over these things?
From supersymmetric localization, I believe, I'm not sure if it's a proof, but basically there's not much more that you can do. The only thing you could do is squash the force sphere. But I believe that Michael and Concau have shown that if you compute this guy, the other guy, and the one in which you also take some derivative with respect to the squashing parameters, these two are the only two measures that you get for this particular 4-point function. What you can do, and I believe Permuter is working on that, is studying O2, O2, OP. Basically in the same format as in here. But O2, 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 I believe these are the only two combinations that you can get from supersymmetric localization. I should say again, this O2, O2, OP was actually done in this paper in here. The fact that a suitable combination of derivative of testoon gives you a certain integral of O2, O2, OP. But for O2, 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 I believe only these two can be obtained from supersymmetric localization. Yeah. So perhaps it's not a lot of data. Yeah.
I saw Michael's hand up.
Why are you asking me questions?
Just a very quick comment. Just a quick comment in reply to Hugh's first question. The formula on the showing there makes it manifest that it's crossing symmetric, because the correlator, the integrated correlator, is simply a mass derivative of the partition function, which is by definition crossing symmetric. So.
This measure is way more complicated. So this measure I was saying, I think is just like crossing symmetric ratio of U and V. This contains this D111 box diagram. So it's a way, but both of them are very well-defined measure, but you have to fold it into the region of convergence. Yeah.
If you consider simply laced groups, so tau equals I is the self-dual point, do you see any interesting structure when you look at your tau equals I?
Excellent question. Thank you. Yeah, well, what you see, actually, I should have maybe put the plot. So for example, for SU2, we can actually compute numerically this one. Tau equal to I and tau equal to e to the 2 pi I over 3. Those are the sort of not self-dual, but you know what I mean, the sort of most symmetric. So you don't really see that much different. What you see is that I is actually a saddle, and e to the 2 pi r3 is a global maximum. This, and there are some connection with. There was a paper on what is string theory, where if you actually compute the maximum of some of these corrections in higher derivative, it's bounded by one of the Eisenstein I was saying. But in terms of values, we didn't spot anything particularly nice. Yeah, we just spotted, of course, like, you know, just by symmetry argument, you knew that they had to be either a local minima or a local maxima or a saddle. What it happens actually, the cusp is the minima, I is a saddle point, and e to the 2 pi over 3 and its friend e to the minus 2 pi over 3 are actually maxima. Yeah, thank you, Jeff. Yes, Amina.
So at some point you mentioned a result about some exponentially suppressed correction. What is the statement? Is it, I mean, one type of correction you can discuss is if you have the perturbation series under control, and then you're saying it's the next exponentially suppressed correction, or is it that you have an asymptotic series and this is something to correct it?
Yeah. So if you wish, let me go there. Perfect. Excellent. So if you wish, this is your asymptotic series, and now you're doing a resurgence in n. You fix tau. So all of these Eisenstein are numbers now. As expected, the genus expansion is supposed to be an asymptotic expansion.
And how do you calculate that?
Oh, very good. So for us, we took the large n expansion of this one. For Yasuyuki, Hatsuda, and oh, where did it go? For Hatsuda and Okuyama, where are they? Here we go. Perfect. For Hatsuda and Okuyama, what they did is they took the result at fixed lambda. The fixed lambda genus expansion is an asymptotic expansion in n. You can use resurgence property, they did it numerically, to actually estimate the size of the exponentially suppressed corrections.
So you have to calculate the first so many perturbation coefficients.
Exactly. Yeah.
I have another question, if I may. So the top line over there is an exact formula.
It is.
Okay. How much control can you if I ask what's the value of C at tau equal to some point, can you, with what accuracy can you calculate it?
Numerically?
Yeah.
Oh.
Meaning, are those interesting numbers? Like
an error. We did calculate it numerically. The worst control is coming from this lattice sum. I believe if you really want to do numerics properly, probably the spectral function decomposition is easier because you don't have any lattice sum. You just need to do an integral over the critical strip, real part of s equal to a half. Honest answer, I've not done the numerics with high precision enough to spot any nice number. Yeah. Do you expect it to be anything nice?
So the reason I ask, it might be fun to do it because in all the calculations I've ever seen when there are zeta values or anything like that, one can't associate physics to it. It's just the coefficient of a certain thing in perturbation theory. That's not a physical observable. But this is.
Yeah.
So if if there's a statement like that, then
maybe at the point that Jeff was talking about, maybe at I, yeah. But at the cusp, it goes to 0. That's a great number. At I, I'm afraid, I mean, we did a plot. I produced a plot. So of course we did numerics. I truncated it some to some high values. And it is of course like this defines an analytic, this defines a real analytic function. And it's non-holomorphic, but it's perfectly good and convergent in upper half plane. Yeah. But yeah, short answer is no, I don't know.
I just wanted to remark that sum on the board there, or on the screen there, is very familiar. It is an example of a Poincare series. And so besides the spectral expansion, in that case, it's easy to compute a Fourier expansion. And each Fourier coefficient is an infinite sum involving Kloosterman sums.
Absolutely.
Dirichlet series.
Absolutely. I'm well familiar with that. We have some paper with Axel. I should say also, sorry, in here, I focus maybe on the 0 mode, but of course, we did precisely what you were saying. We decomposed into Fourier modes, and we checked in the instance of sector against the Krasov and so on. Yeah.
Good. We'll have one last question from Axel and then take a brief break before the next talk.
So I just wanted to ask for this correlator. I mean, you use the mass deform theory in quite some extensive way for doing this. Can you say something about the massive theory itself? So if you don't put m to 0 in the...
Yeah. So there must be something going on over there, right? So this is that was just the second derivative, right? But then you get the fourth derivative. So clearly there must be some sort of holomorphic, non-holomorphic anomaly equation, something like that, that the massive theory. So the massive theory is not expected to be SL to Z invariant, right? Because of the mass. But somehow these coefficients know something of the theory. I believe these people I was referring to, Fucito, Bilot, and Morales, they had something related to this sort of non-modularity of the n equal to 2 star theory. But I'm not really sure how much you can say. Yeah, it would be really nice. We thought about that precisely because the next guy that one wants to study is D4M. So precisely we say, oh, that's the next order. But something concrete, I'm afraid I don't have. Yeah. Thank you, Axel.
So thanks everyone for the spirited discussion, and thank you again for the very nice talk. We'll begin again at the top of the hour.